Welcome grade 12s to PSI Geography Classroom. I am your instructor, Mr. P. Mbuyisa. I am very much happy to have you guys in my classroom once again. We are continuing with our online sessions that we've had. I hope you've put time aside to watch session 1 and make a few notes for yourself. Session 2 as well, to make a few notes and sort of note down the rules that we apply in geography. And now I hope we are all happy and excited to have our third session. Now, the third session again is part 3 of the grade 10 and 11 revision. So in this session, we are basically focusing on how can you individually apply all of the rules that we've discussed in the previous session. So we'll be looking at the actual content you've done in grade 10 and 11, and we'll be focusing then on how does that content that you've done apply in grade 10, in grade 12 work, and what are some of the things that you need to remember and be equipped with for you to do really well in the climatology section in grade 12. So our session outline, as you can see, shows us that the first thing we are going to do is look at the types of cyclones and anticyclones. So that's the first thing we'll discuss, and then we'll move on now to looking at the global air circulation system. So we'll start by looking at global pressure belts. We'll then look at the symbiotic interaction of the arrangement of winds. So we'll look at what does that mean, and how, or rather some of the things we've discussed in the previous grades on this. We'll then look at the tri-cellular arrangement of air. Then we'll look at the intertropical convergence zone. How does it fit into the picture? Then we'll think about Ferrel's law. Again, you'll remember in the previous session we've spoken a bit about it. Ferrel's law and the Coriolis force, what they state and how they apply. And lastly, we'll then look at how all of these things influence the global climatic conditions that we will have in the environment. So without wasting any time, let's get to it. So as we said, the first part of the lesson focuses on cyclones, right? Now, I think it's important for us to just redefine what a cyclone is. It's very important for you to know this, especially for your grade 12 climatology content. Now, a cyclone, remember, is a low pressure system, and we said this system is associated with warm, moist, less dense rising air. So you see now, we are sort of applying all those rules, and we are putting them into context. So cyclones are low pressure systems associated with warm, moist air. Remember, one of the rules we've discussed said that warm air is mostly moist. And we also looked at the relationship between density and temperature. Since the air is warm and moist, it then becomes less dense. And because it's less dense or less heavy, it means now it is always going to rise. And we also discussed that warm air will always converge. And why does it converge? Because it's in a closed, it has a closed system circulation format, which means air will always come to a central point, right? Yeah, so in a low pressure system or a cyclone, air will always converge as a result. Now, what are some of the associated weather patterns? You must note that low pressure systems are associated with unstable weather conditions, which bring precipitation as a result. So unstable weather, it's when we have clouds and wind and precipitation as a result. That's unstable weather. And we know that unstable weather is mostly dominant in summer. So low pressure systems are dominant in summer. So the diagram below is showing us exactly that. You'll see that air is converging towards a central point. So if you look at those arrows, air is converging to a central point as it rises. And you'll see that as it's converging, it's also circulating in a certain way. So that's what happens in a low pressure system. Now let's just look at some of the examples then of cyclones. So they include mid-latitude cyclones. And this is a diagram showing us what a mid-latitude cyclone is. And you see that it is associated with, remember we said unstable weather, and you see that there is a band of clouds over there. It shows us that this is a low pressure system. We also have tropical cyclones as examples. So this is a picture showing us what a tropical cyclone is, and again you can see that something common about it is that it has clouds as well, showing us that we have unstable weather. And a thermal low, now a thermal low will be found on land. A thermal low is also known as a heat low. So that's one example of a low pressure system. We also have a coastal low, and as the name suggests, the coastal low will be in the coastal regions. Hence, I put in a picture of South Africa and a low pressure at the coast. Now we also have a cut-off low. Now I just want us to look at what a cut-off low is briefly. Now a cut-off low only forms when a mid-latitude cyclone breaks apart. Remember, mid-latitude cyclones is formed by two things, a warm front and a cold front. So a cut-off low forms when a cold front is cut off from the mid-latitude cyclone. So what will happen is that this cold front will move over land, right? And as you saw in that animation, that's what the cut-off low is. So it's just a cold front that has been cut off from the system. So I hope you understand that. And when it moves freely, it brings these clouds with it. It brings these clouds with it from the cold front, cumulonimbus clouds, and we are going to have unstable weather in the eastern part of the country during winter. We'll look at how these actually form in detail in the sessions to come. Then let's think about what anticyclones are. Now, anticyclones are basically the opposite. Anticyclones, firstly, are high pressure systems. And what are they associated with? They're associated with cold air that is dry. Remember, we said cold air is mostly dry. So it's an application of the rule we have discussed. And we said that in a high pressure system or an anticyclone, remember now it takes us to the relationship between temperature and density. We said they're always going to act opposite to each other. So since the temperatures are low or the air is cold, it means that density will be high, which means high pressure systems are associated with dense sinking air. So they're associated with more dense sinking air that diverges. And why does it diverge? It's because high pressure systems have an open circulatory system, and hence air always flows out of the system with an anticyclone. And we say they're associated with stable weather conditions because we don't really have cloud cover forming and no precipitation being formed as a result. So you must remember that point. And we know that now they will be dominant in winter, because in winter it's more colder. So they bring these cold conditions in winter. Now, some of the examples, of course, include the Kalahari high pressure, which is also known as the continental anticyclone in the southern hemisphere, the South Atlantic high pressure, which is also known as the St. Helena anticyclone, and the South Indian high pressure, which is known as the St. Mauritius anticyclone. And remember, guys, remember, it is important for you to put that south, because we refer to these conditions or these specific anticyclones in reference to our position, which is us living in the southern hemisphere. So that's what's in your syllabus, what the anticyclones we find in the southern hemisphere. So please always remember that. Now let us then move on to looking at applications, more applications. And this introduces us, of course, to the global air circulation system. Now, remember now that the global air circulation system is formed due to all these rules we've discussed on the behavior of air coming into practice. So when we look at how all of these rules, the horizontal movement of air, which is rule 12, and the vertical movement of air, which is rule 12 as well, leading to us having the formation of wind or air current, sort of influences the global winds or the global pressure belts that we're going to have. So it's really the application of that. And you must remember that now, since at the poles it's cold, we always have the highest pressure there, because remember that when temperatures are low, what happens to the pressure? Remember the relationship between temperature and pressure, they will always be opposite to each other. So since the poles will get oblique rays from the sun, as they will get oblique rays from the sun, or a skewed rays from the sun, it means now they will have the lowest temperatures. And when temperatures are lower, we tend to have what? We tend to have the highest pressure over there. So at the poles, we'll have the highest pressure. And the opposite is true at the equator, because it gets direct sunlight from the sun. So what will happen is that we will have the lowest pressure at the equator, right? And now what will then happen is that pressure gradient will come into effect, because remember, pressure gradient force, what does it says? It basically tells us that air will always move from a region of high pressure to low pressure. So our air will move from a region of high pressure to low pressure. So it moves from the pole to that. But you must take note of the fact that we also have some lines of latitude in between the equator and the poles, and you were taught about these in grade 11, so which takes us to the diagram here on the side. So here at the equator we have our intertropical convergence zone, or the ITCZ, and at the poles you have your polar high pressure and another polar high pressure in the southern hemisphere. And what will happen then is that after that high pressure in the 60-degree line of latitude, you have the subpolar low pressure, and soon after that you have the subtropical high pressure. And remember, it's because of the alternations that state that air will move from a region of high pressure to low pressure, from the polar high, sorry for skewed writing, to the subpolar low, and from the subtropical high to the polar low, and from the equatorial low pressure, or ITCZ, you see, so from the subtropical high to the ITCZ, or the equatorial low. And you also have the same happening in the northern hemisphere. And something that I want us to just take note of is that we have some winds, right? We have some winds, and in the polar region we have polar easterlies. In the subtropical region we have the prevailing westerlies, or we can just say the subtropical westerlies. And next to the equator or the tropical region we have the tropical easterlies. So there is also an alternation of these winds per pressure belt. So it's something we need to take note of and remember, of course. That in the poles, now just to summarize, as we said, the poles are cold, and therefore we'll have what the highest pressure there. And since the equator is hot, we will have the lowest pressure where in the equator, because it is hot. Now, as pressure and temperature act inverse or opposite to each other, the pressure gradient force will influence the pressure of the internal belts. These are the internal belts, the subtropical high and the subpolar low. And what will happen is that air will always move now from a region of high pressure to low pressure, and that is influenced by what? The pressure gradient force, PGF. Sorry for the stupid writing, I'm using my mouse, but I hope we get the point. So we have our pressure gradient force influencing how air will move. Now let's just build up on this. Now, because of these relationships, we say we have a symbiotic interaction of the arrangement of winds. And what does that mean? It means that these winds work with each other. Or rather there is an interaction between all of the global winds. And what are they? The first ones are pressure belts. Remember that pressure belts, guys, are built by air, because remember in climatology we are always looking at the behavior of air. So we are basically thinking about the air that is found in specific regions, and those regions we call the pressure belts. And we also think about the interaction between the global winds and the tricellular cells. And remember, your tricellular cells are your polar cell, your mid-latitude cyclone, your mid-latitude cell, and the Hartley cell, including the intertropical convergence zone, or ITCZ, or equatorial low. So those are the winds that are in play with each other. Now, what is the polar cell? And maybe let's start there. You must note that the polar cell is the smallest and weakest of all the cells. So it extends between 60 and 70 degrees north, or we can just say it extends from 60 to 90 degrees north and south of the poles, right? Now, what you must note there is that then air in these cells, which are the polar cells, always sinks. And why does it sink? Because we have the highest pressure over there, right? It sinks over there and it flows out towards the lower latitudes at the surface. So what we can also say is that at this cell, Ferrel's law is mostly applicable, or the Coriolis force is mostly stronger over there, right? Simply because we have surface winds which can move over the surface. We also have the Ferrel cell. The Ferrel cell is also known as the mid-latitude cell. So the mid-latitude cell is found in the mid-latitude, as you can see. And remember, why are we saying those are the mid-latitudes? Just think about it in this way. We have the equator and we have the 90-degree line of latitude over there. So the 90-degree line of latitude, which are your poles. The equator is at 0 and the the polar high is at 90 degrees. So what will happen then is that if you look at your pressure belts, the 30 and 60 degree pressure belts are at the center, at the central point, at the middle, or at the midpoint. Hence, the cell that is found there is known as the mid-latitude cell. Are we fine with that? So it's known as the mid-latitude cell as a result. Now you must take note that the mid-latitude cell or the Ferrel cell is the smallest cell. It's the second smallest cell. And why do we say so? It's because in this cell, air flows polewards. So it flows towards the poles and eastwards near the surface. It means our air at this side will be flowing towards that direction. Let me use a laser towards that direction. As much as air in a polar cell will flow towards the equatorial regions, and you'll see that these two air masses are of different moisture and different temperature. So there are a sense of disturbances that form when these two air masses meet, and we have systems that are known as mid-latitude cyclones forming as a result of that, which we are going to discuss in the sessions to come as they form part of grade 12 content. For now, you must just remember we have the mid-latitude cell, and where air flows polewards, and you must also take note that the movement of air in this cell is the reverse of what will happen in a Hartley cell, right? So since air flows poleward, it means in a Hartley cell air flows towards the equatorial region. And we say that these winds pick up moisture as they travel over the ocean. So they pick up moisture as they travel over the ocean, which means they bring this warm, moist air when they meet with cold polar dry air. And at around 60 degrees north and 60 degrees south, they meet what? They meet the cold air, as I said, which has drifted from the poles. Now the warmer air from the tropics is lighter. We know that warm air is less dense. So since it is lighter, then it means now the cold air will be more dense. So what will happen is that when the two air masses meet, this warm air will be propelled to rise when the two air masses, the cold polar air and the warm subtropical air meet, and as a result, as I said, we'll have a formation of a system known as a mid-latitude cyclone that we will talk mostly about in the grade 12 content in the sessions to come. So for now, you must just note some of the characteristics of the mid-latitude cell. And what I'm trying to show you now here is that these air masses have a symbiotic interaction. So they depend on each other, they interact with each other, and this allows for different weather or climatic conditions to form as a result. Then the last cell we talk about is known as the Hartley cell. Now in a Hartley cell, you must take note that air rises up into the atmosphere at or near the equator. So the Hartley cell is found near the equator between 0 and 30 degrees. Now what will happen is that this air flows towards the poles above the surface of the earth and returns to the earth's surface in the subtropics. So what will happen is that this air will flow back towards the equator. So in a way, what this is telling us, I know it sounds really weird what I'm explaining, but what this is really saying is that we will have air moving from the equator to this region, because remember, air moves from high pressure to low pressure, and this air may return backwards as well depending on the influence of jet streams. Remember that. So that is what will happen. Now, what is important then is that this flow of air occurs because the sun hits the air at the Earth's surface near the equator. So what will happen now is that we are going to have a lot of rising air, and that's what forms the ITCZ, or the intertropical convergence zone. So it makes this air to move vertically. So at the equator we have more vertical air. So it means we have air current at the equator, vertical movement of air because of rapid evaporation, and we don't have the sideways movement of air. Hence, we say at the equator, or between 0 and 5 degrees Celsius, we do not have the so we do not have the Coriolis forces influence over there. So please remember that for examination purposes. We are going to talk about that when we look at the formation of tropical cyclones. For now, this is just what you need to remember and understand. And remember that for you to understand the symbiotic interaction of the winds, remember, it simply means, now remember, in a symbiotic relationship simply means everyone benefits, right? So for you to understand this symbiotic relationship of air, or how global air circulation will work, you need to first understand or remember your golden rules, because these golden rules are the ones that influence how the air will behave in a high pressure belt, in a low pressure belt, and how it will behave in the different cells, because it follows basically the same rules. Now, let's just build up, or just look at a cross section of the winds, the tricellular arrangement of the winds. Now, by definition, the tricellular model is a simplified explanation of how atmospheric circulation patterns will give rise to distinct, please take note of that, distinct or different weather patterns and climatic conditions at various latitudes. So it's based on the principle of the uneven heating or differential heating of the Earth's surface. So because of that, we have different patterns, different cells forming as a result. Please remember that. Now, this is a cross section of the Earth basically. Remember, the equator will have the 0 degrees over there, the central point, and after that we'll have your 30 degrees, the 60 degrees, and the pole, which is 90 degrees, right? Over there. Now, at the equator we have our ITCZ, and soon after that we have a Hadley cell, and you see that a Hadley cell is associated with cumulonimbus clouds. And why is that the case? Because there is rapid vaporization happening there, because this region receives direct heat from the sun. So you see why we said this is dependent on the differential heating of the Earth's surface, as we said. So that's what will happen. And if you look at that, we have our cumulonimbus clouds in the Hadley cell. And soon after that, between 30 and 60, we have a Ferrel cell, or a mid-latitude cell. Now, the mid-latitude cell, remember, it feeds over the moisture of the ocean, and we said that air in this cell will flow towards the polar regions, while at the polar cell, air will flow towards the equatorial regions, which means it will flow towards the subtropical regions, and that's what we mean. And it means that this cold air from the polar cell will meet the warm air from the Ferrel cell over here, and we say that a polar front is what forms, right? A polar front is what forms. And what is a front? It's an imaginary line that separates air of different moisture. So it separates air of different temperature and moisture. So since we are looking at the polar front, so it means we are really focusing on the temperature of the air. So we have air from the poles being separated from air from the subtropical regions, air from the poles separated from air from the subtropical regions or from the Ferrel cell. And when these two air masses meet, remember cold and warm air do not mix. What will happen is that the cold air will sink, because based on the rules we taught you or we have discussed, cold air will always sink because it is more dense. Remember the relationship between temperature and density. And as a result of that, we are going to have the warm air from the Ferrel cell rising. And when it rises, it leads to the formation of cumulonimbus clouds, and we are going to have a mid-latitude cyclone forming as a result. We are going to look at the actual formation in detail in one of the topics, or rather one of the first topics you're going to look at in grade 12 content. So please stay tuned. I think session number 5 will be discussing how that happens. So please take note of that. For now, let us just understand how these winds will interact with each other. So basically, the tri-cellular arrangement of air looks at how air will behave in a Hartley cell, how it will behave in a Ferrel cell, and how it will also behave in a polar cell. So I hope we understand that. And remember that in a Hartley cell, we have tropical cyclones forming. They form due to air rising rapidly, because remember, these cyclones form in the tropical regions, hence they are known as tropical cyclones. So the second topic we are going to do in grade 12 will be looking at that. So for now, I hope we understand that. Let's just move on to then looking at how does Mr. ITCZ filter in this whole story. Now, before we even look at the nodes themselves, you must remember this small thing, and I'm going to try to draw a small diagram here. So this is the Earth, right? I'm sorry for how skewed it is. So this is the Earth, and this is Mr. Sun, right? Now, if you have the Earth and you have the Sun over there, you must note that, remember that the Earth is at a tilt, right? At a tilt, and it means that now the equator will be skewed to that direction, right? So what will happen now is that the Sun will always give direct rays to the central part of the Earth. Now your ITCZ will be located there basically. So the ITCZ is located there. Now if you look at it now, if this were the Sun, and let me just erase, and yeah, let me just use the color yellow for the Sun and shade it around. So if this was Mr. Sun, yeah, I think this works better. And Mr. Sun is giving direct rays. Mr. Sun is giving direct rays to the central part of the Earth. So this is more direct, and oblique rays, of course, to different parts. And you can see now, because of that, it means since the southern hemisphere is getting direct rays, it means it's summer in the southern hemisphere. So what will happen now is that our ITCZ will be in the southern hemisphere. And why do I say so? So let me just use a color. So because of that, remember the equator is already skewed. So it means this region that receives direct rays will form our ITCZ, the intertropical conversion zone. And what does that mean? Remember, we say that the intertropical conversion zone, or what is abbreviated as the ITCZ, is a region that circles the Earth where near the equator. And you'll notice that they did not say at the equator. It's because the ITCZ migrates with seasons, so it's not always at the equator, but it is near the equator. And so if you look at it, that was our equator. Right? Because the Earth is tilted, the equator is somewhat skewed a bit. Now it means the ITCZ will always strictly face towards the Sun. Right, and we say that this is a region where trade winds of the northern and southern hemisphere come together. So the trade winds, remember the trade winds we spoke about. So they come together, they all flow towards this region, which is the ITCZ. Now you must understand that the intense sun and warm water of the equator heats the air in the ITCZ, and it raises its humidity. Now, as a result, this region will have a low pressure, and this low pressure will cause humid and rainy conditions when it's over an area, and it causes droughts now to move away. Now, all of this, guys, is in the name. You see, it's called intertropical convergence zone. Now, intertropical simply means inter means at the center of something. So it's at the center of the tropical regions. And we say it's a convergence zone. And what systems are associated with air convergence? We said those are low pressure systems. So low pressure systems are associated with air convergence, which means the intertropical convergence zone is associated with low pressure systems. And I can also ask, in which season are low pressure systems dominant? And you will respond to say they are dominant in the summer season, which means the ITCZ will always go to the hemisphere where it is summer. And now it takes us to the diagram here. Now, if you look at it, it shows us the positioning of the ITCZ. So in the southern hemisphere, the ITCZ will be there in January or around January. And why is that? It's because in January in the southern hemisphere it is summer, while in the northern hemisphere around July it is mid summer over there. So the ITCZ will migrate depending on the seasons. So let me just show what will happen in the northern hemisphere. There is our Mr. Sun again. Guys, I'm using a mouse to write, so that's why this is skewed. Now, in this case, we have our tilts towards that direction, and our equator will be positioned in that manner. And this is Mr. Sun again. And remember, the poles will get skewed rays from the sun or oblique rays from the sun, while the equatorial regions get more direct sunlight from the sun. So what will happen is that equator will get more direct sunlight, not the entire equator, remember that, because it is tilted, and the poles will get more skewed rays. And if you look at that now, going back to what I described before, you'll see that this region, section of the or part of the equator gets direct sunlight, and the other part does not get direct sunlight. So that's where your ITCZ will be positioned in the northern hemisphere. So it is a region basically that gets more direct sunlight from the sun. So please remember that. I hope you understand what I've explained. And this happens in the northern hemisphere. Remember that in the northern hemisphere, this happens in July, which is midsummer, while in the southern hemisphere, this happens in January, which is our midsummer over there. So the ITCZ will always migrate with seasons. And remember, when it migrates with the seasons, it also migrates with the anticyclones. Because remember, when it comes to the southern hemisphere and meets the anticyclones that are found at the 30-degree line of latitude, which is the subtropical cyclone, or sorry, the subtropical high pressure belt, what will happen is that these pressure belts are pushed further south. And why is that? It's because warm air and cold air do not mix, but they meet. So hence these systems are pushed further south when the ITCZ chooses to move to the southern hemisphere due to the earth heating the southern hemisphere more directly. So please remember that, which means in winter, when the ITCZ goes to the northern hemisphere, because it will be summer over there, it pulls or it allows for these anticyclones to go back to their area of origin, which is the 30-degree line of latitude. And we'll explain that more in depth when we look at tropical cyclones again, and mid-latitude cyclones and subtropical anticyclones. We look at that ITCZ shifting story even more. But this is how the best I could explain it. Sorry for the skewed diagrams, but I hope we get the point. Now let's move on. Now the laws now that in a way determine how our air or our global winds will behave is firstly the Ferrel's law, right? Now, Ferrel's law is a law that was coiled or first named after an American meteorologist known as W. Ferrel, who lived from 1817 to 1891. Now, it's a rule that basically states that air or water moving horizontally in the northern hemisphere is always deflected or pushed to the right of its motion. And again, it also states that air or water moving horizontal in the southern hemisphere is deflected to the left. And now, this deflection of this air is influenced by the Coriolis force, right? So that it is influenced by the Coriolis force. And what is that force? The Coriolis force is known as the apparent force that results from the Earth's rotation. So the Earth's rotation leads to the deflection of moving objects such as projectiles or air currents. Remember, air currents is vertical movement of air. So the Coriolis force will then deflect this vertically moving air to the right in the northern hemisphere. Remember that, right where northern hemisphere, and to the left where in the southern hemisphere. So basically the force, Coriolis force, follows Ferrel's law. So Ferrel's law says in the northern hemisphere, air will be deflected to the right. In the southern hemisphere, it will be deflected to the left. And what influences that deflection? It's a force known as the Coriolis force. So the Coriolis force implements what Ferrel's law says. So the two work hand in hand. So please remember that. So about that. So please remember that. So let's move on now. Since we've looked at these global winds, the forces that come into play, the different cells in the tri-cellular arrangement of air, now we need to then look at how do these winds influence the climatic conditions at different parts of the world. And that is very important for you to know, so that when you are asked what impact does this have on humans, you can also just sort of think about how are the different atmospheric conditions at different parts of the earth, and how does that get influenced by what? By the different global air systems, right? Now, at the equator, as we said, the equator receives oblique rays from the sun, as you can see. You see, they are more skewed, they are not direct. And because of that, they are not direct. Now, it means that our air going into the equator will be more skewed, right? Or rather, our insolation going to the equator will be more skewed. And as a result, the equator is very cold. And because it's very cold, a lot of cold air will sink over there. So the air is very dry as well. So it has very little moisture, and as a result, very little precipitation will be experienced over there. And because of that, because of these extremely cold conditions, plants cannot grow, because remember, plants have to have to perform photosynthesis, so they need to have sufficient or enough heat from the sun for them to grow, so they can't really survive at the poles. Those are the effects of the winds over there. Now at the 60-degree line of latitude, remember, which is the subpolar low pressure. So what we have there is that the warm air from the lower latitudes. Which lower latitude? So we're basically looking at the warm air from here, from the subtropical region. So remember, this air flows towards the poles, right? So this warm air from the lower latitudes meets this cold air. It will meet this cold air from the poles, and this leads to the production, or it leads to precipitation forming, and as a result we can have forests forming over there. So because of precipitation, the conditions are more or less favorable. So we can say in this region there is a balance between warm and cold air, and the climatic conditions are thus favorable for life. So plants that need more colder conditions can survive, and plants that need more warmer conditions will survive. Those that need water will survive, and all of that. And a typical example is the conditions that will be experienced in South America, right? In the continent South America. So they are located more or less closer to that 60-degree line of latitude, including parts of Australia as well. So those are the conditions that you will have over there. And at the 30-degree line of latitude, we have dry air sinking over there. Remember, that's the subtropical high pressure belt, and high pressure means cold air, and cold air means we have air sinking, and air sinking means this air is more dense, and more dense air is usually dry, right? And as a result of that, we are going to have this dry air sinking. So that's where you'll have little rainfall, and that's why you have the Namibian desert and the Kalahari desert occurring in this region, right? So that's the 30-degree line of latitude, and remember, this line passes over Southern Africa, or South Africa to be specific, and it also has an influence then in our weather conditions in summer and in winter. So those are the conditions you'll have. Now the last line of latitude you'll have is the equator. Now at the equator you have warm, humid air, warm, moist air, and we said warm, moist air always does what? It rises. Why? Because it's less dense. So as this air rises, it will cool down, and when it cools down, it condenses and produces a lot of rainfall. So hence we say those regions are tropical regions, because it's always raining, and we have our rainforests as a result. So I hope we can see that the rules we discussed, or the geography laws or rules we discussed, influence all the content we look at in geography, and they influence the biosphere. They influence how the lithosphere and biosphere are gonna be. So I'm sure you can see now that the atmosphere or the layer of gases we discussed in the previous session is very important, because it influences how the other spheres are gonna turn out. So remember the first rule: when we look at climatology, we are basically looking at how the air will behave, and how this air behaves influences how the other spheres will turn out, how the lithosphere will turn out, how the hydrosphere will turn out, and how the biosphere will also turn out. And the opposite is also true. These spheres may influence how the atmosphere will turn out, and in turn it will lead to global a full-on or fully fleshed form global air circulation system, and as a result it leads us to us having meteorologists and climatologists making predictions based on observations that have been done in the long term to sort of try to understand why climate is the way it is at different latitudes and why the environment is the way it is at different parts. And that's what you are supposed to know and understand from this section of work. Now let us summarize. In summary, now you see that our summary is just this diagram, and this diagram is basically applying all the rules, because it shows us that we have the intertropical convergence zone, and the convergence zone, air conversion is associated with what? Low pressure systems, and low pressure systems associated with warm, moist, rising air, right? And it means now at the equator you'll have that air. Now this rising air will lead now to the formation of a Hartley cell, which forms between 0 and 30 degrees, which is associated with tropical rainfall and tropical cyclones as a result. And we also have the mid-latitude cyclone forming as a result of the mid-latitude cell, which forms as a result of westerly winds, warm westerly winds meeting cold polar easterlies or easterly winds. And where do they meet? They meet at the line 60 degrees, which is the polar front, leading to the formation of rainfall and leading to forests forming over there and rainfall as a result, of course. And we also have the polar cell, which forms in the polar regions. Remember, the poles are really cold, so they are uninhabitable. And why is that? Because they receive uneven sunlight or oblique rays from the sun, and therefore there is little to no precipitation over there, and it is really cold. So you'll have your polar high pressure over there. And remember now that our air or our global winds will follow, the pressure gradient force that states that air will always move from a region of high pressure to a region of low pressure. And the interchanging lines of latitude, they have different pressure. They have air of different pressure. So at 30 degree you have your subtropical high pressure belt. At 60 degree you have the subpolar low pressure belt, and at 90 degrees you have the polar high pressure belt, and at 0 degrees you have the equatorial low pressure belt, or the tropical low pressure belt, or the intertropical convergence zone. And remember, the intertropical convergence zone is a zone that is formed due to the equatorial or the mid regions of the earth receiving direct sun rays from the sun. And you must note that between 0 and 5 degrees, the Coriolis force does not have a strong effect over there, because we have a lot of air current due to rapid evaporation and condensation, leading to rain formation over there, which is suitable for rainforests forming at the equator regions. And remember that now from 5 degrees to 90 degrees, we have the Coriolis force being in effect over there. And why is that the case? Simply because of Ferrel's law, which states that winds will always be deflected to the right in the northern hemisphere and to the left in the southern hemisphere. So that's what I have for us today. That's how the laws apply. They apply even more now in the specific systems that form as a result of these global winds that we are going to study intensely in grade 12 content. So for now, I would like to sign off again. Coming up in our next session, we'll be looking then at communication. Basically, we'll be looking at communication of information in geography. And we communicate information or our knowledge using synoptic maps and satellite satellite images. So we will be looking at how satellite imagery assist us to represent these different systems that form, and most importantly, how can you analyze these synoptic weather maps for examination purposes, or how can you really read them for understanding so you can apply and describe what is happening at different parts of the world, and how can you also do the same with satellite images, and so that's what we are going to be looking at intensely. So please join us in the next session. For now, you can take time to rewatch the video if there are parts that you didn't really understand. And you feel free to also drop questions in the comment section. I'll be open to responding to any of them. For now, I am signing off. See you in the next session. Thank you very much. This is Mr. Pimbuisa again, signing off. Enjoy the rest of your day. Bye.
Audio Jungle.